From Cambridge University Press in collaboration with The Naked Scientist, this is episode 10 of the Cambridge Prisms podcast, addressing real-world challenges in research and discovery. I'm Chris Smith. This month, the shot in the arm that AI is administering to the drug discovery industry, how do you measure the microplastic problem, and how models can help us to stay one step ahead of flood risks. First though, there is an important mantra in conservation biology that if you don't understand a species, you have no hope of saving it. But in Australia, as Jess Marsh at the University of Adelaide and John Wernowski at Charles Darwin University point out, the problem isn't just one of known unknowns, it's also unknown unknowns. There are thought to be literally hundreds of thousands of invertebrate species across that continent, but only a fraction have been scientifically documented. So if they were to go extinct, who would know? And moreover, how many are going extinct? Well, thanks to this new study, we now think the answer is a very alarming number. And to reach this conclusion, they have taken the approach of using extinction rates of animals that we do know more about and applying those to the invertebrates that we don't yet know about.
In Australia, there's an estimated 320-odd thousand invertebrate species. So the invertebrates are the slugs, the snails, the insects, the spiders, basically the animals without backbones. But only around a third of them are described. So for many of them, we actually don't know much about them at all. We don't know where they are. We don't know what's threatening them. Currently, only 10 invertebrate species are officially recognised as having gone extinct. And this seems too small compared to the huge number of species we've got and also the threats that we know are impacting them. And so in this study, we really set out to try and work out how many invertebrate species have likely gone extinct in Australia.
It's a huge country, John. That's not a small undertaking. How have you tried to do it?
It's challenging, of course, because there's so little data for many of these species. What we tried to do was we took two approaches. One was to get the proportion of extinct species in well-known taxonomic groups like mammals, birds, reptiles and the like, and then apply that proportion similarly to the number of invertebrate species in Australia. And the second approach we took, which was complementary, was we looked at the proportion of extinct species of invertebrates globally, and then applied that to Australia as well. And they came up with much the same results, that about 9,000 invertebrate species have become extinct in Australia since 1788. Clearly, it means that we've had far greater impact on Australian environments than was hitherto recognised. We also calculated the rate of extinctions that's occurring currently, and our calculation was that between 1 and 3 invertebrate species were becoming extinct every week.
And what do you think the drivers of those extinctions are?
There's a number of threats that are impacting invertebrates. Many of them are interacting and cumulative, kind of amplifies the impact of other threats. So one of the key threats that's happened is habitat loss and clearance, which has meant that species are being forced into smaller and smaller areas, and there's a reduction in movement between areas. As well as that, there's large-scale use of pesticides, there's introduction of feral animals and weed species, all of which degrade habitat, break it down, make it less suitable for animals to survive in there. And then, of course, climate change. Many invertebrate species are at high risk from climate change because they need high humidity and lower temperatures. And so all of these threats, which have become bigger with increasing human population sizes, are impacting fauna.
And in many cases, the invertebrates are far more prone to extinction because invertebrates, more so than birds or mammals or reptiles, often have really small ranges, only a few hectares. There's the entire range of some of these species. So even a little bit of clearing will have the possibility of knocking out that species entirely.
There's presumably also, John, this thing that we humans tend to obsess about the big things, the very visible things and the cuddly things. And we tend to overlook the smaller things that we may have an aversion to, like the spiders I know that Jess loves. And so as a result, we tend to overlook some really important elephants in the room.
Well, not elephants in this case, slugs. So the major biases in our treatment of nature, we care far more about those charismatic mammals, pandas, koalas and the like than we do for invertebrates. There's far more knowledge about mammals and reptiles than there is about invertebrates. There's far more conservation management directed at mammals and birds and reptiles than there are about invertebrates. So there's a whole series of elements of neglect that are affecting invertebrate conservation. We feel that we should be more egalitarian in our treatment of nature. Invertebrates really do matter. Our lives depend upon them more so than koalas. We're trying to actually redress the balance and take out some of the biases in conservation thinking and planning, and also community awareness about nature.
The thing that you've stated, though, where there are measurable numbers of species disappearing on a weekly basis, A, that's very alarming, but B, this is actually flying in the face of the Australian government have said they want to stop all extinctions. Now, is that just sort of words to get elected, or have they actually made meaningful efforts and they're just failing?
Oh, look, it's a really admirable and egalitarian pledge to try to prevent any further extinctions. The trouble is with the invertebrates, we really don't know which species are the most imperiled and most in need of conservation. It's just the huge amount of ignorance we have about the invertebrate fauna in Australia and generally across the globe. So we don't really know where we should be addressing our effort. There are some clues, though. We know that many of the invertebrate species are narrowly endemic and that a whole lot of species of invertebrates co-occur at these centres of endemism. So if you can help identify where those places are and help protect them, that will go a large way to protecting many of our most imperiled invertebrates.
Have you got a strategy for that, Jess? Because obviously, as the old saying goes, if you want to conserve something, you've got to know about it and understand it. And if we don't know about a lot of these things, you can't really draw up policies to protect them.
Yeah, absolutely. And it's a key problem in Australia. We need to address the knowledge gaps. I think we almost need to look at invertebrates in a different way than we treat mammals and reptiles and the better known taxa in Australia. As John mentioned, those centres of endemism are important, but we don't know where they occur. So we need to work out where they occur. We need to work out what's threatening them and also how we can protect them. And I think with invertebrates, from the general public right up to government and conservation decision makers, there's a general ignorance about them, their lives, the things that are threatening them, and also their importance to us as humans. So it's double-edged. We need to find out more. We need to work out how to protect these areas, and we need to protect them. But then we also need to try and change this belief or this lack of awareness of the invertebrates and of their importance. They are really important for our natural world, for our agriculture, and for our ways of life. And I think losing 1 to 3 species a week, it's a wake-up call that we need to change something and try a new approach.
2 extinctions in a week. Wow. Jess Marsh and John Wernoski there. An unarguable fact about the modern era is that we are awash with data. And when it comes to healthcare, the same applies, particularly since countries have moved over the last decade onto electronic patient record systems. This means we have massive health libraries that we can trawl for new drug leads. But, paradoxically, we've gone from a paucity of information to a situation where we now have so much data that processing it meaningfully is becoming a problem. And this, Aaron Wentler at Queen Mary University of London argues, is where AI and machine learning is coming into its own, especially when it comes to drug discovery. Seeing biochemical needles in haystacks is what this technology is supremely good at. And in the next decade, we should, as a result, see our successful new drug hit rate climb, partly by helping us to refine our choices of targets.
One of the biggest challenges in drug development is that many clinical trials fail. And this is not only because drugs are poorly made, but generally this is because they target the wrong biology. So either the target, the biological target, which might be a protein or a gene, isn't truly involved in the disease. And in fact, a large portion of clinical trials can be traced back to the initial choice of a drug target. So in this review paper, we essentially asked, how can we harness AI with all of this massive amounts of biological data we have access to in order to improve drug target discovery and validation?
The pharmaceutical industry argues that it gets it right about 10% of the time, because we talk about the sort of number 10 cropping up a lot, don't we? 10 years, 10 billion to get there, and about 10% of the time we actually end up with a drug that works. So you're trying to improve the odds with the use of AI.
Yes, exactly. That's exactly right. This is predominantly motivated by all this wealth of biological data, genomics data, proteomics data, clinical records, you name it. With so much, there are many ways in which we can use it better in order to inform target discovery.
Where's the missing link then? Given we've already got all that data, what are we doing wrong that means we're not hitting the nail on the head more often?
That's a very good question. First of all, we are very much in the early stages here with breakthroughs in AI that recently have empowered us to do certain things that simply before we couldn't. And we actually see that AI is already being used nowadays for many different biological modalities, be it genomic sequences, protein structures, or even biomedical literature with large language models nowadays. I think for biology, one of the big missing links is the fact that we need to integrate all these different modalities. And that's something that is not being done as much yet, but it's something that people are working on.
Are you saying then that we've got all of the building blocks, all the data are there, but as humans, we find it really, really difficult to see the associations, the links, how to join the dots when there are literally millions of dots? And this is something that machine learning / AI type systems are actually really good at. They can spot those sorts of patterns and therefore see what we can't.
Exactly. And not only that, they allow us to spot these patterns across different types of biological data. We have come to appreciate just how multimodal biology is. That means that there are different moving parts on different scales on the cell level, on the tissue level, on the DNA level. And by integrating all of this data, which is something that machine learning allows us to do, and then spotting patterns across these different types of data, which is also something that AI excels at, we can build applications useful for drug discovery.
We've got to train it though, so it knows what to goal seek towards. So when you're doing something like this, how do you train it?
That's a great question. And that, of course, depends a lot on what you're trying to do. So, one example would be if you are trying to look at electronic health records, oftentimes you have a big data set, generally spanning tens of thousands of patients. And then you train your model on this data. This actually brings about certain problems and biases that also need to be addressed. So, for example, a lot of these big data sets that we use to train these models are representative of just a small fraction of the population, oftentimes. And so we need to make sure that these data are sufficiently representative of different strata of our population in order to get the best possible models that benefit the most amounts of people. At the end of the day, your AI or machine learning model is only as good as the data that you use to train it.
Indeed, because it can spot associations, but it can't see things that we haven't discovered yet. So there's still going to be a place for adding to the data to do research. So can it guide us towards gaps in our knowledge? So as well as saying this might be a target, can it also highlight areas where our knowledge is deficient? And if we reinforce that, it may open up new vistas to explore.
Right. You're spot on there. I think that is how we need to think about AI. Nowadays in the media, you often hear about these sort of future visions of what AI might allow us to do and that it will replace humans in the workforce, for example. We are not at that stage. And how we should and could use AI as of now is exactly like you say, sort of explore the boundaries of what we already know. Have AI guide us in the right direction simply by spotting patterns that we ourselves or different types of algorithms cannot do.
What do you think the timeline is for this? Because it sounds lofty and a wonderful thing to aim for, but it also sounds like a huge amount of work to make this happen meaningfully.
Yes, definitely. It's difficult to give exact numbers on these types of questions, but what I can say is that we are already seeing that AI is currently making impact. In our paper, for example, one of the things we did is that we mapped out the progression of current drug candidates that were proposed by so-called AI-first drug discovery companies. We found dozens of compounds that are, at the time of writing of the review, were going through clinical trials. So that's sort of a proxy of the impact AI is already having. So in the coming years, 5, 10 years, if you want to be a bit more conservative, I expect we'll definitely see AI make a significant dent.
Aaron Wendler there. This is the Cambridge Prisms podcast, and I'm Chris Smith. In a moment, why the water industry needs to worry about climate tipping points. But before that, though, it's now just over 20 years since the word microplastic was coined by marine biologist Richard Thompson from the University of Plymouth. And over the intervening 2 decades, we've realised that these small particles of plastic are ubiquitous in the environment. As he put it, we don't know they're everywhere, but everywhere we look, we find them. In fact, scientists estimate that there are about 14 million tonnes of plastic particles already sitting on the seafloor, and one of the worst offenders for putting them there is the fashion industry. This is because historically it's been very difficult to assess consistently which fabrics shed more or fewer plastic particles when worked, worn or washed. But maybe that's about to change, because Lisa McIntyre at Heriot-Watt University has developed the world's first visual grading system that uses a 5-point scale to assess very quickly by eye the volume of fibre fragments that are shed from different clothing materials. She's hoping to make fashion labels and consumers more environmentally aware when manufacturing and buying new clothes.
When I first started investigating microplastic testing, there were no standard test methods. The methods that they were using were time-consuming, and we did a couple of pilot projects with a couple of master's students, and the results were really illogical. And so I wanted to come up with an easier, quicker, more reliable method for measuring the results.
Why do we need to measure it? If we know there's a problem, why do we need to know how much of this there is?
Without measuring the fibre fragmentation that comes from textiles, you can't design better fabrics, and you can't do any quality control testing that would pick good fabrics instead of bad fabrics. We reckon that about a third of microplastics in the environment have come from a textile source.
Wow, that's a lot, isn't it? What is it about the textiles that produces them in such abundance then?
We use them all the time. We wear textiles, we go out into the environment wearing textiles, we use them in our homes. So it's partly prevalence that textiles are a huge part of what we use as humans, and that plastic textiles makes up more than half of all the textiles that we use and wear.
But with so many use cases, there must be so many different routes to produce plastic wear particles. They go in the washing machine, they go on my back, they go under other clothes, they get used to do other things. All those must be a route to producing a microplastic. So how can you standardise that?
Well, you can't. And at the moment, we've only really addressed microplastic testing for wash tests. And that's because the first work that was done to identify microplastics was done by marine scientists. So the first places that they were reported were in marine environments or rivers.
How are you trying to do this then? What was your approach to come up with a less laborious but heavily reproducible and easy to do mechanism to give us some kind of insight into what the likely plastic burden from any given item is going to be?
Early wash tests for fibre fragmentation were based on washing the textiles and then filtering the liquid that comes out of the washing machine. The fibre fragments were captured on a filter paper, and the filter paper was weighed before the test and then after the test. But the textiles are producing very tiny weights of fragments. And in the early work that we did on this, we found really illogical results. And sometimes we were seeing either zero fibre fragment weight difference between the before filter and the after filter, but we could actually see the fragments with our naked eyes. There wasn't a logic there. And so we first established that that wasn't working very well. And the other method that was used in the literature was counting fibre fragments. And again, in the early work, people were doing manual counts of fibre fragments, and we looked at that and found that that was incredibly time consuming. 2 to 20 minutes per grid square on a filter, with more than 30 grid squares per filter. That was clearly going to take far, far too long for anybody to use that in a commercial environment. And then we thought, well, we could do machine counting because machines are brilliant at counting things. But the machine counts that we got were incredibly variable. And that basically depended on how you set your boundaries for the counting device. You can kind of filter and tell the computer what to count as a fragment and what not to count. But depending on how you set those boundaries, you could get it to count half of what a human counted, up to 5 times what a human counted. And no single boundary setting worked for multiple samples. So basically, you could get the computer to tell you whatever you wanted it to tell you.
Sounds like the story of my life. How did you solve it?
So in textile testing, there is quite common use of a 5-point visual grading scale where observers compare the appearance of the test sample to the appearance of a 5-point grading scale. And that's used to measure colour change after wash and staining of adjacent fabric, the amount of bobbling on a fabric, the amount of creasing on a fabric. So basically, when I very first started looking at this, I had a notion that surely that would be better. So the very first time we got test results that were illogical from the weighing method, I thought, oh, we could use a visual scale for this. So back in 2020, we started a PhD project to fully quantify the problems with counting, fully quantify the problems with weighing specimens, and then to set about developing 5-point visual scales and then test them.
Does this actually enable us now to say, well, the problem is now solved? If everyone embraces your method, how much time is it going to carve off? And what degree of standardisation will it actually bring? Does this solve the problem?
Our method is much quicker than the counting method and the weighing method by orders of magnitude. So our method takes about, for a set of 3 test specimens, each observer can grade that in 3 minutes. And we recommend 3 observers grading 3 test specimens to get 1 result per fabric. To manually count, you're looking at between 1 and 5 days. You're reducing the amount of time by at least a factor of 10.
Lisa McIntyre. The infrastructure that means that we can turn on a tap and fresh water flows out takes massive planning and considerable amounts of time and money to install and maintain. In sum, it is not an agile industry. Building a new reservoir can take many years. The problem is that climate change has the potential to upset the apple cart because change can come very rapidly and very dramatically. This is referred to as a tipping point. Things remain stable for a very long time, and then some threshold is breached, and then things change very far, very fast. More or less rain may arrive than anticipated, and temperatures can climb or sink far farther than we're prepared for. And if the water industry can't keep pace, we may be in big trouble. This is the thrust of the analysis that Peter van Tienen from the KWR Water Research Institute has carried out.
Climate tipping points are these thresholds where you push the system a little and it will change a lot. So for example, a big ice sheet, you start heating the atmosphere and it will melt a little bit more, but it will still be the same ice sheet. But at some point you cross a certain boundary and it just completely melts away. So this is what we call a tipping point. And we see that climate scientists are talking about this a lot. We see also that they are not well represented. They seem to be not well presented in climate models. And as a result, they are also not included in climate scenarios that everybody is using to plan their futures. So I'm working in the drinking water industry. And what we see here is that we are a very slow moving industry by necessity. I mean, we build infrastructure that is meant to operate for many decades and often even longer in practice. So we really need to think ahead. And that's why it's really important to understand these tipping points, because they may cause changes on a much shorter timescale than we're used to dealing with.
Why do you think that, despite talking about them extensively, climate models capture them so poorly?
That's because they are not completely understood. They are the result of a complex interaction of many different processes. And it's probably also a matter of model resolution. So the detail with which you can model the processes. So they're not intentionally left out, but they are very difficult to model adequately.
So what are you proposing as an alternative, or how do you propose to surmount the problem?
We need to recognize that these tipping points may have significant consequences. So that was actually the objective of our paper, to evaluate how relevant these potential tipping points could be and what their potential consequences could be for drinking water provision.
And when you say you've looked at the potential impacts of them, how have you done it? What's been the approach here?
We started out by just doing a review of the scientific literature on tipping points and describing what's going on there. Then we tried to make an evaluation of the confidence levels of how these tipping points are represented in Earth system or climate models. Then we try to make an overview of the climate hazards that may result from these tipping points and what their impacts would be on water sources, on abstraction, on treatment, on distribution. And we also try to make an overview of possible mitigation or adaptation measures.
How did you identify them in the first place? So I know you've given us the definition of what's regarded as a tipping point, but how did you actually then say, right, I'm going to go and find the representation of that tipping point and its possible impact in the literature so we can put that one down and say, well, we've now gauged the potential risk from that one?
So we are basing ourselves on the climate science literature, which provides overviews of what are considered to be possible tipping points. And then we try to answer a number of questions. So for each of these tipping points that have been identified, we tried to answer the question, how strong would its effect be? How long would it take to start? And how long would it take to complete? So actually combine these questions, more or less describe the risk for us or the possible imminence and effects of such a tipping point.
And how many do you think there are of them that we really need to worry about?
Well, there's actually two that we probably really need to consider. And that's the AMOC, the Atlantic Meridional Overturning Circulation, of which the Gulf Stream that provides us with a mild climate in Europe is part, and the associated system of the Labrador Sea or subpolar gyre convection. And these are two somewhat deviating tipping points, so to say, because many of the tipping points that we know in Earth's climate system, they would result in a heating of the atmosphere, a more rapid heating, warming of the atmosphere. Whereas these two, at least on a regional scale in Europe, could result in a cooling of our climate.
And how will we know when we've breached them? And if we do, what will be the impact?
So there are climate scientists and oceanographers are working on identifying early warning signals for the activation of these tipping points. And actually, there was a paper published 2 years ago which predicts that the AMOC might collapse somewhere later this century. So the result of that would be a significant cooling over Europe, up to several degrees if we look at the annual mean, but maybe more in winter, so we could get very cold winters. We would also have a drying of the continent, less precipitation here, and sea level would also rise by 30 to 100 centimeters, possibly over a relatively short period of time. And in addition to what is already happening because of the melting of ice sheets and things like that. So that would impact the availability of water in Europe for the production of drinking water and for food production. It would also impact the quality of the water, in particular in coastal areas, because we would have additional intrusion of salt water. And it would also affect our infrastructure because our buried pipes are quite sensitive to freezing of the soil, to freeze-thaw cycles and things like that.
Therefore, having identified these as critical points that we may be approaching, can you make some recommendations so that we can safeguard against this? Are these likely to be surmountable challenges?
In terms of the water practice, I think it really needs to be aware of these tipping points and needs to consider tipping scenarios, in particular this AMOC collapse, when planning infrastructure. And this means that there is a wider range of uncertainty with respect to our future climate conditions. It may go one way, but it also may go the other way. We may have warming and drying, or we may have cooling and drying. And that requires, to some degree, different measures of adaptation. So it is really important that the water sector closely watches as the early warning signs that are developed and monitored by the climatology and oceanography communities are monitored. And it's also quite important that they move from a very rigid and robustness-focused approach to building infrastructure, something which is that meant to last for 50 or 100 years, to a more flexible approach. It is obviously quite difficult for drinking water distribution networks, which are buried in the ground. And once they're there, it's really a lot of effort to replace them entirely or to move them to deeper levels, for example, in order to prevent them from freezing.
Thought-provoking stuff, that, isn't it? Peter van Tienen there from the KWR Water Research Institute. Extreme storm surges and flooding in their aftermath can devastate coastal communities and ecosystems. To avoid catastrophic impacts and losses of lives, we need to be able to anticipate when this is going to happen and prepare accordingly. Models are a key tool in helping to forecast events like this and to understand how they evolve, gauge their potential impacts, and also support recovery efforts. But, somewhat surprisingly, and as a rule, these models are generally not often implemented, even where they could reasonably be deployed. One extreme surge that occurred recently in the German Baltic Sea has afforded scientists the opportunity to test the utility of these sorts of models and develop a framework for using them effectively to manage extreme coastal flooding in one region. This has enabled Nassos Vafidis from the University of Kiel to identify 3 phases before, during and after the event and suggest the specific actions that need to be undertaken in each phase.
Our motivation was the October 2023 storm surge that hit the German Baltic Sea. It was a rather extreme event with a frequency of occurrence of 1 in 200 years and constituted a great opportunity for us to test our numerical models and collect data on flood characteristics, which are very rare.
How extensive was the data collection? What did you actually measure?
Our work is mostly focused on modeling, and we use models to, for example, estimate the frequency of occurrence on these events. So we look at past events, we look at the tide gauge measurements, and we try to estimate how often these events occur. This is difficult because there is only 30, 40, 50 years of data in the best of cases, in most places at least, and we're trying to predict occurrences of events that happen once in 200 years or once in 500 years. So we need to model these data. Historical information from scripts or novels or hearsay can reduce the uncertainty and improve those estimates. These estimates are essential for designing coastal protection. We also saw that extreme water levels can vary considerably spatially, and the existing networks of tide gauges do not capture this. So models allow us to produce results at much higher resolution, and this can also be used for coastal protection estimation, but also for responding.
So that gives us the upfront preparation. What about the opportunities afforded when the event is evolving in real time? What can you learn? Because that presumably is a high priority to learn from a real event as it unfolds. So what do you prescribe is the sorts of things we should be doing during the event itself?
Absolutely. I mean, I have to point out it was great to have real-time information about how the extreme water levels would evolve in the next hour or 2 hours. And this was based on simulations, and this is available and people have access to this. But we can do more. All this information kind of tends to stop at the coastline. So we have no information how the actual flooding might evolve. We can forecast that pretty well, either by looking at maps or maybe even running models in real time. We're not fully there yet because these hydrodynamic models take a few hours in the best of cases to run, depending on resolution. But there are simpler models that we can use and forecast how the flood on land will evolve. The other thing, which is pretty difficult to do, is collecting data during the flood. This helps us improve our models. And it's notoriously difficult because, few people want to go out, a few crazy scientists want to go out during the flood event and start measuring water depths. But we have now instruments that are relatively cheap, such as pressure sensors, for example. We have satellites, we have drones that can give us information during the flooding. And this information can, be used for, emergency responses, but also can be used to improve our models, calibrate them, tweak them in a way that they can represent the events as accurately as possible.
And in the aftermath, what sorts of things should be on the priority list to measure then?
Assessing impact is a priority. We need to respond quickly. We need to help. So rapid mapping, assessing the flood extent and depth, flood characteristics in general, assessments of damages depending on water depth can be very quickly produced with model simulations or with measurements. And of course, all this information can also be used going back and evaluating the work that we did in preparation for such events.
Is the purpose of this that you produce something which is bespoke for one geography, or is what you're saying, we do this, we demonstrate with this one geography how integrating these different bits of information, the before, the during and the after, produces a model way to approach this sort of problem, and then we extrapolate that to any geography that may be affected in the future?
This is a very interesting point. So our intention is to propose a framework for making this information more accessible, more systematic, more understandable, but also to produce actionable knowledge. So obviously, in Germany, we have access to a lot of data, computational facilities, which allow us to run models quickly. But there are elements of the things that we're proposing that are available everywhere, and they are becoming increasingly available. Also, the capacity to do these things is rapidly evolving. So eventually, this kind of framework can be used in any other place, and it can also be populated with the elements that already exist. That would be good enough to start.
How will it cater, though, for the future? Because we anticipate that with climate change, extremes of weather are going to become a lot more common. And also that general weather patterns are going to change anyway. So therefore there's a two-dimensional change potentially coming, and any system we set up has got to be able to cater for that.
Absolutely. I mean, this framework is flexible, so it allows, going back, or actually you have to, after an event, go back and reevaluate what you've done before the event. Flooding will become increasingly intense in the future just because of sea level rise, even if weather patterns do not change. And we need to prepare well for a wide range of scenarios. We also need to prepare for scenarios such as dike breaching, for example. We know that defenses often fail, and this can have catastrophic effects for coastal communities. So all this preparation can take place in the context of this and can be organized in the context of this framework and be constantly updated. So I would say for the future, such frameworks are essential for being able to manage and to cope with such events.
Nassos Vafidis there. And that's where we're having to leave it for this episode. But if you'd like to follow up on any of the references and the interview transcripts of the papers we've been hearing about in this edition of the programme, then please head over to nakedscientist.com/prisms, where you can also find out how you can subscribe to this podcast on the off chance that you don't already. And if you've got some science to publish, why not submit it to the journals today? Maybe you can become our next guest here on the Cambridge Prisms podcast. I'm Chris Smith from The Naked Scientist. Thanks for listening, and until next time, goodbye.